Hello, dear attendees. I am Domenico Ciuonzo, and I work as a tenure-track professor at the University of Naples, Federico II from Italy. My expertise falls within IoT, data fusion, AI, network analytics, and sensor networks. First of all, I would like to thank the TSP organizing committee for this kind invitation. In this video specifically, I will provide a keynote which provides an overview to the design of next generation network traffic classifiers via the use of artificial intelligence, specifically deep learning. This is a quite challenging and timely topic which attracts both the interest of academia and in the industrial partners. Now let's move to the content of the keynote. In detail, I will first spend a few words describing the context of mobile traffic, pointing at the important task of traffic classification. I will then mainly focus on mobile traffic classification. I will introduce the application of multimodal deep learning to mobile traffic classification, which is very interesting. And the objective is to address the design of classifiers able to deal with the heterogeneous nature of traffic. I will then focus on the issues of data availability and reproducibility, which are essential in the use of data-driven techniques. Then I will provide the first shot on the beneficial use of explainable AI tools to make traffic classifiers trustworthy and also possibly improve them. Subsequently, I will discuss how adaptivity can be encoded in traffic classifiers. And to this end, I will focus on the case of incremental addition of new applications, which may come into a store, into the classification task. And finally, we'll end with some take-home messages drawn from the reported findings. First things first, why should we care about trying to draw analytics from mobile traffic? The reason is that mobile traffic now represents a significant share of the traffic generated by devices connected to the internet. And this is, of course, highlighted by many annual reports like those from Ericsson, Sandvine, and so on. Hence, the design of resilient and self-healing internet relies on the intrinsic knowledge that we obtain via network analytics from such huge bulk of traffic. And of course, this corresponds to the perception step in the cognition cycle, which is the stepping stone towards autonomous networks, before taking any reasoned action or control. This trend is also reflected in our everyday life. For instance, during and after the pandemic years, we have been massively using collaborative apps for working and doing remote meetings like Zoom. This is also done in many video calls. Video on-demand apps such as Netflix for entertainment, and also social apps to get engaged with other people like TikTok, Twitter, Twitch, and so on. And this shift has also dramatically changed the complexity of the applications, which are now becoming multi-activity. And for this reason, to face with the composite nature of mobile traffic, we are in need for associating traffic flows, namely a sequence of packets which are being carried over the network with mobile applications that have generated them. Okay. And this is what network traffic classification is about, which is the subject of this session. Clearly, there are a number of main drivers or motivations for performing effective mobile traffic classification. Such drivers mainly pertain to the main pillars of network management and user profiling. Indeed, such classification info may be either leveraged by infrastructure operators or advertisers for totally legit reasons, for instance, enhancement of the quality of experience. However, the invisibility info can also raise some privacy issues because they could be applied to network surveillance and to derive some sensitive information. For instance, just think about e-health apps or apps used by children. Unluckily, the situation has significantly changed, and now performing traffic classification, especially that of mobile devices, has become quite a nightmare for many reasons. Hundreds of applications are currently used by mobile users, and just think what you could find on could find on the Play Store. Also, each application has its own peculiarities, and a bunch of trending applications emerges almost every week. This is our common everyday experience. The same app may generate different traffic depending on the device and the operating system it is installed on. and also its current version. And there are updates every week, of course. Many applications also use common third-party services, which make the identification more challenging. For instance, just think about the APIs of Google Maps. And such traffic has become almost entirely encrypted. Of course, the network traffic classification problem is not new. Indeed, since the early years of internet, this requirement was highly desirable for management of the networks. However, during the 90s, performing traffic classification was relatively easy. Okay, indeed, you could look at destination port or inspect the payload or do both and achieve almost ideal performance. For that reason, technical challenges were mainly related to implementation or efficiency aspects. However, payload inspection has the drawback of being expert labor intensive because you need to define the signatures, and also computational intensive because at different stage. And this is why machine learning came to the rescue roughly in 2004. Yet the rise of encrypted protocols and privacy concerns prompted for exploring alternative solutions. Also, machine learning found application of statistical flow features and flow counters, or their compressed forms, which served as the input for the traffic classifiers. For this reason, almost 20 years ago, both the academia and the network players started tackling the problem of traffic classification by means of machine learning algorithms based on statistical features extracted from a given aggregate of traffic. And the above design was based on the well-known two-step phase, where you have the first phase in which you define a bunch of meaningful statistical features, and then you have the second phase where you design a proper machine learning algorithm for classification, which is based on this feature set. However, this approach has been recently shown to have some serious performance limitation in the case of mobile traffic. This is because in the dynamic landscape of today's internet, the effectiveness of existing traffic classifications approach faces new challenges. To address such growing complexity, researchers have pursued the adoption of deep learning techniques to mobile traffic classification. The clear objective was to avoid the step of feature design, which is handcrafted and time-consuming. Indeed, by training end-to-end feature extraction and classification phases, so this means that you are doing both at the same time, deep learning models can achieve state-of-art performance and also enable expert-free operations. This is a great promise for tailing the fast pace and the dynamic nature of traffic we want to classify. Sadly, or luckily, depending on the viewpoints, despite the achievements in deep learning traffic classification since 2015, which is the first paper which appeared in the literature tackling traffic classification with deep learning, there are still a number of open challenges today. As a whole, these challenges all actually represent the missing link toward product line implementation of traffic classifiers, which are based on AI at scale. And this keynote specifically addresses two of these challenges, as I'm detailing in what follows. The first challenge is that traffic classification solutions based on deep learning are entirely designed to be end-to-end. And since they are data-driven, these automatically make them black boxes. However, network operators need to understand why a classifier took a specific decision and also how much reliable are its outcomes, and also whether this could be improved. And also, all these key aspects are also pushed by regulators. For instance, just think to the recent AI Act of the European Union. The second challenge is that deep learning techniques are computational intensive and time consuming. And this aspect is exacerbating the network traffic classification. This is because new apps or services come out very frequently. And this implies that if a new app or service needs to be included in the visibility process, a full retraining of the classifier is needed to account for the new classification space. And for this reason, in this context, I will discuss the concepts of trustworthy AI, which is intended to address the first challenge. In other terms, we want to design traffic classifiers with interpretable behavior and whose confidence can be relied. And class incremental learning, which belongs to the more general framework of continual learning. This allows to add new knowledge, in our case, add new classes, to a deep learning model which is already trained without retraining everything from scratch. The starting point of my discussion is the description of what currently is the state of art in traffic classification based on deep learning. Specifically, in recent years, multimodal deep learning emerged as the fundamental tool to cope with the heterogeneous and the multifaceted nature of the network traffic. And specifically in our group, we came up with the framework proposal, which is called Mimetic, which is a catchy acronym for multimodal deep learning based mobile traffic classification, which is a general specification of a multimodal deep learning architecture for traffic classification. Going into the details, Mimetic is fed with P different inputs, the modalities, for each traffic object to be classified, with each modality processing a different part of the network data by means of the corresponding input extraction block. Such deep network architecture is firstly composed of a number of single modality layers which are input specific. So there is a branch for each modality, and these layers extract discriminative feature pertaining to a given view. And this is done in increasingly abstract fashion. Hence, these branches capitalize the intramodality dependence of the features of the inputs. Then the abstract features are joined by a merge layer, and the latter represents the first layer channeling the modality-specific information toward the joint multimodal representation. Okay. This architecture is finally completed with a few shared representation layers, distilling the features capturing intermodality dependencies and the usual softmax layer, which returns the soft output vector. The proposed architecture also relies on a training procedure which is made of two phases. The first phase is called pre-training, where each single modality stack is first pre-trained independently, that is without the shared representation layers, by topping each modality chain with the softmax layer stub. And the second phase is called fine-tuning. The softmax stubs are removed, and the training of the whole mimetic architecture is performed after freezing the parameters of the lower layers. This two-stage is intended to distill discriminative information from each modality so as to capitalize the advantage of the multimodal traffic representation. Our multimodal proposal, Mimetic, was compared on traffic classification of Android and iOS mobile apps, which was provided by a global provider under NDA, and was shown to outperform four different classes of baselines, which are described in the slide. The first one is the best single modality deep learning classifiers, which are fed with either one of the two inputs that we are considering in our multimodal architecture, which are the first 576 bytes of the byte flow, or the first 12 packets. And the second baseline is a shallow multilayer perceptron with only one hidden layer, which corresponds to a lower bound on the achievable performance, which is trained on the same inputs. A flow-based random forest, which was the state of art in traffic classification based on machine learning, and classifier fusion techniques, which combine the best single modality deep learning architecture, which represent the first set of baselines, and this type of combination is based on either hard or soft fusion techniques. What's also interesting is that the multimodal architectures not only reach higher classification performance, but they also show lower complexity than its main competitor, which is a 1D convolutional neural network based on the sole payload input. And this is highlighted by considering both the runtime per epoch, which is the left figure that you see in the slide, and also the overall number of trainable parameters, which is expressed in millions on the right, of the implemented distance of mimetic and the considered architectures. And this is mainly due to the simpler, this means computationally lighter layers, which are involved in mimetic instance, allowed by an improved capitalization of the inputs available. Although interesting, we obtain these results on private datasets. Also, in other case, there are publicly available datasets, but those are bot generated. And for such reasons, our group at the University of Naples has devised and implemented a reproducible architecture for generating mobile traffic and also obtaining the corresponding output, which pertains to the mobile app that has generated it. And this has led to the Mirage project. And in this case, our objective is to foster reproducibility and further advances on the topic by the scientific community. Specifically, Mirage is implemented as a collection and ground truth generation architecture. Indeed, with our architecture, real users can connect with their mobile devices to an USB hub, and this hub is also a capture server, is connected to a capture server, which is able to collect all the traffic generated by the users and also to associate the right type package which is associated to the traffic. The experimentation to a few hundreds of users in our lab has led to the corresponding Mirage 2019 dataset, which we have publicly released. This dataset is generated by 40 different Android applications, which are labeled by flow level. So for each by flow, you have the corresponding label. And each app belongs to these 16 different categories from the Play Store, from Google Play Store. Per packet data, per flow features, and per flow metadata are reported for each by flow in the dataset. And for those of you which are interested in performing mobile traffic classification, you may refer to the URL at the bottom of the slide to download the Mirage 19 dataset. Additionally, I would like to highlight that the Mirage 2019 dataset can be also used for experimenting with other analytics related problems like fine-grained mobile traffic prediction. What's really important is that this is an ongoing project, which means that there are two newer datasets, which are called Mirage Video and Mirage COVID CCMA, which are specifically focused on video apps and collaboration apps, which have been recently released by our group in the last 2 years and can be also downloaded. And also a newer version of the latter dataset will be released in the next few months, which is specifically focused on apps which perform activities. Reasoning on the proposed numeric architecture and in general on multimodal proposals for traffic classification, what it is really disappointing is that they work quite well, but we actually don't know why. So it is of interest understanding what's going on into such black box. However, understanding the internal behavior of neural networks is not only useful to interpret and justify their behavior, but also to troubleshoot and improve them, of course. For this reason, in recent years, there has been a widespread adoption of so-called explainable AI techniques for network traffic analysis. And among the different techniques proposed, there is no general framework and there is a lack of consensus on which technique is better. However, post-hoc techniques are the more used in the literature due to their appeal in explaining models that are already trained. So these are useful because you are not stick to a specific model. Accordingly, our explainable AI-based analysis framework is defined as follows. For each tested traffic object, in our case by flow, we obtain an explanation by means of the well-known Shapley values of the confidence associated with predicted application. In our analysis, we focus on when the classifier recognizes the generating app correctly, which means that we are analyzing the correct behavior of the classifier. Once you obtain the explanation in terms of the importance values from SHAP, we normalize them, and this is because we want them to sum to 1 and attribute the same influence to each by flow explanation. And then we obtain a global explanation for the classifier by pulling the single explanations and taking the median value of the importance value, because the median is a robust summary statistic. By applying the aforementioned methodology, we are able to investigate 3 relevant hidden patterns of mimetic. First of all, by aggregating the explanation over the whole dataset, we are able to assess to which degree each modality contributes to a correct classification. And by looking at the results, in the case of mimetic, it is apparent that the payload modality is predominant in recognizing the correct app, while the PSQ modality, which means the informative fields of the first 12 packets, is only marginally exploited. We have 17 versus 30 importance share. Secondly, by aggregating over specific application, not on the whole dataset, and by looking at the results obtained only with the payload modality, it is apparent that the considered number of bytes seem to encompass all the information needed for accurate classification. Of course, this depends on specific application, and for instance, if you look at Dropbox on the left, you can see that the attribution as a more structured and shorter payload dependency with respect to Spotify and Trello. Thirdly, a similar comment applies by looking at the packets, at the fields composing the PSQ modality, where all the information seems to be contained in the first 10 packets. Of course, also in this case, the behavior specifically depends on the specific app. And for instance, in this case, Facebook requires much less packets than Trello and Hangouts. The previous analysis has underlined that there is a diversified behavior by varying the application, but there is a clear imbalance in the contribution provided by each modality. And for this reason, we devised an improved version of the mimetic architecture, which is named mimetic enhanced, which has three key differences as underlined in the slide. First of all, one embedding layer is provided for each input. This is to make the network able to fully extract information of each modality without exaggerated focus on either. The second advancement is that to support a graceful multimodal training, we have adopted an adaptive learning rate in the sense that the latter parameter is added every given number of epochs, so as to avoid instability on training. By looking at the traffic classification performance of mimetic enhanced, we can see that it outperforms all the existing baselines, ranging from 3 base models, which are DT in the table, to state-of-art multimodal classifiers, including our previous mimetic proposal. Also, the achieved accuracy gain is quite general, and this is apparent from the radar plot at the bottom left of the slide, and applies to different protocols running over the transport layer. This includes also QUIC, which is commonly used by Google applications, and Facebook Zero, which was used to Facebook apps till a few years ago. It is of interest understanding what it is so special in the behavior of mimetic enhanced to be able to outpace mimetic. So we want to understand why mimetic enhanced outperforms mimetic and what's the reason. If we compare the modality contribution with our SHA-based analysis, it is apparent that mimetic enhanced relies on a more balanced fashion of the modalities. Indeed, there is a lower gap in their distribution importance, as you can see at the bottom of the slide. In other terms, mimetic enhanced is able to truly capitalize multimodality as opposed to mimetic. This trend is again quite general, because you can look at the protocol breakdown, and this explains also the general improvement of different protocols of the previous slide. The second question is aimed at understanding how much deep learning, including multimodal deep learning architectures, are reliable. In other terms, is their confidence a reliable measure of the traffic classification process, which means that does, for instance, 90% confidence for Hangouts means that 90% of the times by flow is generated from that tab. In this respect, the calibration diagram, which is reported in this slide at the bottom right, allows understanding whether there is an optimistic or a pessimistic behavior or a break-even classifier. Hence, it turns out that multimodal deep learning classifiers, despite being better calibrated than single modality, still exhibit an over-optimistic behavior. And for this reason, to improve the reliability of our multimodal solution, we have explored two noteworthy techniques. The first one is based on the so-called focal loss. In this case, you have that the modification relates to a change of the classification loss used to train the architecture. Indeed, in the place of the well-known categorical cross entropy, we use a multi-class version of the focal loss because this was originally conceived to deal with the class imbalance. But it has been shown that focal loss can be also interpreted as a classification loss as a cross entropy loss plus a regularization terms, which depends on the entropy of the confidence vector. Thus, this promotes less optimistic or spiky outcomes. It is worth noticing, of course, that when you set gamma equal to 0, this corresponds to the usual cross entropy approach. The second one resorts to so-called label smoothing. And in practice, during the training phase, the one-hot encoded ground truth is not used purely, but it is mixed with a uniform distribution via parameter alpha. This avoids that the trained classifier tries to emulate the hard output of the ground truth, and this promotes, of course, a more prudent outcome. And also, in this case, alpha equals 0 provides the usual cross entropy with no label smoothing training. And we now assess the reliability of magnetic enhancing in terms of the expected calibration error by applying the two described solution. To this end, we assess the calibration sensitivity by varying relevant parameters in focal loss, which is gamma, and in the label smoothing, which is alpha. The calibration sensitivity is depicted in the bar plots on the left by reporting both the results on the whole Mirage dataset, but also the breakdown for different protocols. Since both techniques modify the training process, for each of the considered values, we also report the corresponding accuracy and F measure in the complementary data tables. By looking at the trend over the whole dataset, the red bars that you see, it is first apparent that the expected calibration error shares a unimodal trend, and the optimal lowest values in terms of the calibration metric are obtained for gamma equal 3 and alpha equal 0.25, sorry, for focal loss and label smoothing, respectively. Interestingly, by matching calibration with traffic classification performance, we can notice that the parameter achieving the optimal calibration for each training variant does not coincide with the highest deep learning-based traffic classification effectiveness. So this means that the best calibration configuration does not coincide with the best performance variant. And this is indeed obtained with the gamma equal to 2 and alpha equal to 0.1. And however, the relative loss is very marginal and is less than 0.25% for both the accuracy and the F measure. We then delve into the calibration details of these two variants of magnetic enhanced, which means using focal loss and label smoothing, with respect to tuning the parameters to achieve the optimal calibration. To appreciate the calibration effect of these modifications, we also report the naive, which means the non-calibrated version of magnetic enhanced in the red calibration diagram. The comparison is performed in terms of the relevant calibration diagram associated with the expected calibration error. Given the high performance achieved in magnetic enhanced, it is apparent that most of the classified byflows are predicted with confidence values within the range 90-100%. Hence, in this slide, we show a 10 pair zoom of the calibration diagram for the aforementioned beam. And by looking at this zoom, it is apparent that the non-perfect calibration of magnetic enhanced, when considering both the whole confidence range, but also focusing on the beam 100%. Differently, calibration effect of the optimized focal loss and label smoothing is evident for all the values of predicted confidence. So this means that there is a general calibration improvement. And for instance, as you can see, the adoption of focal loss and label smoothing is able to achieve a six-fold and two-fold expected calibration error reduction with respect to the incalibrated case. And differently, if you compare the focal loss with the label smoothing, you can see that the focal loss achieves the best calibration. And of course, the case can be also appreciated by comparing visually the two calibration diagrams. Because the calibration diagram of the focal loss is closer to the ideal accuracy confidence line. Finally, the left table summarizes the results of the calibration analysis, which is then extended to all the baselines considered to provide a fair comparison. In this table, for both mimetic enhanced and the best performing baseline, which is mimetic, we report the results attained with best calibrated configuration with focal loss and label smoothing, and also their vanilla versions, which means that we are not using any calibration technique. The reported results highlight a clear trade-off between the accuracy of the prediction and reliability of the corresponding confidence. Indeed, in its native formulation, mimetic enhanced has a calibration error which is roughly 2 times higher than that of mimetic. So the calibration of mimetic enhanced is worse than the original mimetic. This witnesses, of course, that improved traffic classification performs based on interpretable methods comes at the cost of reduced reliability in the provided outcomes, and of course, this calls for methods to improve it. The second observation is that calibration improving solutions are less useful when considering an approach which is already well calibrated in its native variant. And this is apparent for mimetic, where only label smoothing is able to obtain a calibration improvement, whereas mimetic with focal loss is even less calibrated than its native formulation. Last but not least, the experimental results witness also that the use of either focal loss or label smoothing, regardless of whether they provide a remarkable calibration improvement or not, leads to an extremely limited traffic classification accuracy decrease, which means that it is less than 0.33% for mimetic enhanced. On the other hand, all the baselines report calibration errors that are higher than mimetic enhanced with either focal loss or label smoothing. And it is worth noticing that among the considered baselines, least calibrated approach is the decision tree, which is the naturally interpretable method that tends to be significantly overconfident in its prediction. And such outcomes, of course, remarks the utility of focal loss and label smoothing to improve the calibration performance, with, of course, their usefulness being more limited when considering an approach which is already well calibrated in its native variant. We now turn our attention to the second requirement of this keynote, namely whether a traffic classifier can be updated with the new apps without a full retraining. Actually, thanks to the advancement in AI, this is possible, and the fundamental set of tools allowing it is called class incremental learning. But first of all, how does class incremental learning compares to a full retraining from scratch? Left and right figures illustrate the training workflow of the two cases. In both cases, at time t, there is a traffic classifier which is trained to discriminate among a certain number of applications. However, after a certain time, a new set of classes, maybe new services or new applications, needs to be included into the classification task. In the usual case, the usual setup, which is called Scratch, which you have on the left, a new traffic classifier is trained with the dataset which includes both byflows from old classes and new classes. On the contrary, in the class incremental learning case, the previous traffic classifiers is updated, so this is in principle computationally efficient, by using only the samples from the new applications. So this is in principle privacy preserving. Actually, I have to say that in the class incremental learning, usually a few subset of samples from old classes is stored to better enforce discrimination between old and new applications. So perfect, let's buy class incremental learning for our traffic classifiers. There is, however, a huge fundamental trade-off which limits the performance of class incremental learning method and make them far from performance obtained by a full retraining case. And this trade-off is depicted by the figure in the slide. Specifically, when we want to update our traffic classifier with the new applications, there are two contrasting trends. The first trend is that your updated classifier maybe not learning in effective fashion the new application. This is called the intransigence phenomenon. On the other hand, your updated classifier may not be retaining the knowledge of the old application, and this is called the catastrophic forgetting phenomenon. Hence, several specialized techniques have been proposed in the literature to achieve the best trade-off between these two conflicting trends. First of all, it is worth noticing that most of the class incremental learning techniques are devised specifically for neural networks because they have appeal and are flexible and can almost naturally incorporate new knowledge. This type of techniques can be categorized in three main families. There are the fine-tuning techniques, the fixed representation techniques, and the model growth techniques. Fine-tuning techniques work by adapting gradually both the model backbone and the head during the incremental learning phase. Different in fixed representation approach rely on a rich backbone, and so they alter only the model head during the incremental phase. Model growth technique instead try to enlarge the model's architecture to accommodate for new knowledge. So they have an architecture which keeps growing as soon as new classes come in. So here our first question was to investigate whether there is a case for class incremental learning in traffic classification. In other terms, is there any class incremental learning technique which can approach the performance of Scratch? And for this reason, we carried out a wide benchmarking, which includes reasonable baselines and state-art techniques from both computer vision and traffic classification, as highlighted by the taxonomy table. By looking at the taxonomy, it is apparent that most of the state-of-art techniques are based on the fine-tuning principle. However, they differ in the way the loss driving the incremental procedure is defined. The general loss is that reported in the slide at the bottom right, where there is a classification loss which focuses on encoding the augmented classification problem to cope with intransigence in issue. And then there are usually also both distillation and regularization losses, which try to make the updated model behave functionally and structurally like the old model to cope with the forgetting issue, so to make them retain the old knowledge. Last but not least, most of the state-of-art techniques are based on the so-called rehearsal process. In other terms, the forgetting of old knowledge is mitigated by retaining some samples of the old dataset in the model update. Of course, when you do so, there is a trade-off between privacy and computational efficiency based on the number of samples that you want to keep, that you want to retain in your memory. And equally important, there is also the same question on which samples should be retained, which means which is the best sampling strategy. With this large pool of state-of-art for class incremented learning, we experimentally evaluated two different scenarios on the Mirage 2019 dataset. The first one is called a big increment scenario, where a traffic classifier is trained with 20 applications, and additionally other 20 applications needs to be incrementally learned. This kind of scenario resembles those typically encountered in computer vision in terms of proportion between old and new classes. The application to traffic analysis would be that of traffic personalization, where you have a given traffic classifier, and this is shared between network operators, and one of the network operators wants to personalize it with the new apps for billing or management operation. In this case, to provide a little bit stable results, we evaluated the performance on 10 cases of random addition of 20 apps, so to stabilize the results. The second scenario is what it is called a small increment scenario, where a traffic classifier with 39 apps needs to encode the additional knowledge of a single emerging app. So you have only one new app that needs to be added. And this is quite peculiar to the relevant situation where you have a network operator that from time to time needs to update traffic classifier with the new incoming apps. And in such a case, we have evaluated performance on the different 14 cases of one app addition. And in this case, we have an exhaustive coverage, sorry, of all the possible combination in our dataset. Finally, I would like to recall that in this benchmarking, we have not used the multimodal deep learning architectures, but rather simple single modal architectures based on PSQ input, such as the 2D convolutional neural network that you see in the slide. The reason is that the class incremental learning problem is very challenging, and we have preliminary found that the class incremental learning techniques need to be to be carefully specialized for the multimodal case in order to for them to work reasonably and acceptably. So we did the steps gradually. Equally important to evaluate traffic classification performance incremental scenarios, it is apparent that differential forms of usual traffic classification for traffic classification metrics are required. This means that, for instance, taking the F1 score as the relevant metric, three meaningful evaluation metrics are what it is called drop all, how much lower is the F measure when a train incrementally as opposed to a full retraining, and ideally I would like to have a drop equal to 0, and also drop old and drop new, which is the same difference, but focusing only on old or new classes. And this is to a certain potential issues due to forgetting or intransigence, respectively. Reporting the results of the benchmark on the radar plot that you see in the slides, we see that all the drops we now report the result of the benchmark on the two radar plots that you see on the left for big increment and on the right for the small increment. And the radar plot is arranged to cover the three previously introduced differential metrics. Of course, these metrics, since are drops, the best results are achieved on the outwards of the plot. And first of all, to better understand the results, we split the methods into two macro classes, namely baseline and state of the art. Considering the baselines, we observe that the best performing methods are the ones that adopt a memory, namely FTMEM and FZMEM. Then comparing FTMEM and FZMEM on the two scenarios, we can see that a big increment scenario leads to a more balanced performance across the metrics, while a small increment scenario enjoys a smaller drop old but a larger drop new. Since we are dealing with F measure, a larger drop new implies a very low F1 score achieved by incremental methods. And this is likely due to the precision, to low precision, and the catastrophic forgetting to hold the sole new app that we are adding. Compared to the baseline, instead, the state-of-art methods have, of course, always better performance. Recall that the lower is the better. And this applies to both scenarios. However, their performance presents characteristics that are similar to that of the baselines. This means that the big increment scenario leads to more balanced performance, while the small increment scenario incurs a higher drop U, which is again likely due to catastrophic forgetting. Hence, despite state-of-art methods significantly outperform the baselines of the previous slide, there is of course a clear improvement. They still present inadequate performance in the small increment scenario. For this reason, there is a huge room for improvement in terms of how to design novel class incremental learning methods in this traffic classification scenario. Now that you have understood how far class incremental learning methods are from full retraining in terms of traffic classification performance, we now look at the other phase of the medal, which means how much do I gain in terms of training time. So which is the reduction of training complexity. For this reason, in the slide, I'm reporting the ratio between the training time needed by the generic class incremental learning method divided by the time needed for full-time training. So ideally, we want this ratio to be smaller than 1. And of course, this analysis is reported for the two scenarios that we have introduced. In the big increment scenario, all the approaches result in a total training time that ranges from 1/4 to three quarter the time spent by Scratch. The only exception is represented by what it is called overhands, which requires 10 times the training time required by Scratch. This outcome is justified by the fact that this is a particular model growth solution, which grows the classification structure with the number of classes. I'm not going into the details, but in particular, the addition of 20 apps requires for variants the training of 20 new one versus rest binary classification models. On the contrary, in the small increment scenario, which is the right plot, we can notice that all the approaches show a total training time which is, in the worst case, 20 times lower than Scratch. This is a huge complexity gain in this peculiar scenario, which I recall you is also the more challenging in terms of traffic classification performance. And in this case, the complexity of overhands is manageable, but this is because in general this scenario better enjoys the characteristic of the incremental learning setup. The final side note is that I have divided the training time in SGD and post-SGD contributions. This is to underline the time need for actual training via the stochastic gradient descent method, and all the preliminary and ancillary operations which are required before starting the incremental training, because most of these methods require preliminary operations before the actual training phase. Referring to post-SGD, in the big increment scenario, the impact of operation is always negligible, while their impact is somewhat higher in the small increment. The reason is that these preliminary operations are associated with the starting model, which is bigger, because in the small increment scenario we have a classifier which is already trained on 39 Naples, and this is why we have a slightly higher contribution of the post-SGD. We can now put in comparison the two phases that I have discussed. On the one hand, the traffic classification performance, and on the other hand, the traffic classification complexity, so the training complexity. And this is done with this plot that puts on the x-axis the training time, and on the y-axis the overall FMH. This is the absolute performance, so this is not drop. And by looking at this plot, you can do two main considerations. First of all the approaches behave similarly when passing from the big increment to the small increment scenario, where you have a general decrease of the total training time, which reduces by 1 order of magnitude at least. Secondly, the analysis highlights that the approaches also achieve a general F1 score improvement, saved from lucid technique, moving from a big to a small scenario. The only caveat is that in the small scenario there is still a relevant gap due to residual catastrophic forgetting. By focusing on the big increment scenario, big results the winner in the 20+20 scenario, with comparable F1 score with respect to lucid and lower training time. On the other hand, in the small increment scenario, the highest training time is achieved by big and overhands, which also share the same F1 score, which is higher than 73%. So this means that in this scenario, you cannot have methods with the highest incremental traffic classification performance and the lowest training complexity. Hence, to summarize this keynote, this keynote has highlighted that multimodal techniques are the current enabler for state-of-art traffic classification. What it is not trivial is that their design is not immediate. I have also discussed the current partial lack of dataset for performing sound experimentation which are related to mobile traffic analytics. And to this end, I have provided you an overview of the Mirage project. And I have discussed very briefly the publicly available datasets that are shared by our group. Then I have highlighted the performance wall of current state-of-art multimodal traffic classifiers and the need for explainable AI tools to in their interpretation and reasoned improvement. Finally, I have laid the ground for instilling adaptivity properties in the deep learning-based traffic classifiers whenever new application or services come in and need to be recognized. Although the results are promising, the analysis has shown that there is a still huge way to go. This concludes my keynote on this interesting topic. I hope you enjoyed it. For those who want to deepen it, I'm collecting a list of references which provides you the general context and more or less the state of art. And also in blue, I am highlighting the contributions provided by our group. That's it. Thanks a lot for listening to the whole story, and feel free to drop me an email for any question or curiosity related to the covered topics. Thanks a lot. And thanks again to the organizing committee of TSP for the kind invitation.